to look at is the precise definition of a limit. Okay, and let me go back to in the history, the math history, the mystery history of calculus. So Sir Isaac Newton is credited with inventing calculus, and then Leibniz is credited with also kind of inventing it at maybe a little bit after Newton. That's the narrative. Leibniz was the first one to publish it though. But anyways, in the beginning, this concept of the limit is important, because here what's going to happen is there's three main things in calculus that you're going to hear about, and the first one is limit, and then there's derivative and integral, and derivatives and integrals depend on the limit. Okay, this concept of a limit. And when calculus first came out, when it was first invented for like for quite a while, their definition of the limit, they didn't have this definition of the limit that I'm about to show you, which is this right here. For every number epsilon greater than 0, there is a number delta, such that and the way that you look at this is right here, is this absolute value of x minus a. That's the distance between x and a. Okay, so they want that distance to be less than delta, but greater than 0. But so greater than 0 means so let me write that. So this right here, this part right here, this part of it means that x is not equal to a. That's all that means. X is not equal to a, which is what we've been saying all along, is the limit doesn't depend on the value at a. Okay, it does not depend on the value at a. The value of the function at a. Okay, or does not depend on f of a, whether even if it's defined or not. Okay, doesn't matter. Okay, so and then here, this part right here is the distance between f of x and the limit L is less than epsilon. So that's the distance between those is less than epsilon. And the way that it's typically illustrated is something like this. So if you have a function f that's going to a particular value, and let's just I'll just make a hole in the graph just for running. That's a, this will be your L. And so the idea is this. So given epsilon greater than 0, that will create what we call a neighborhood about L. Okay, so from L minus epsilon to L plus epsilon. So that's what that is right there. So this translates to f of x being between L plus epsilon and L minus epsilon. Okay, so if you look at this right here, that's what that's going to come down to. Okay, this equation right here is the same as that, which gives you this little interval right here. And the idea is that you come out here, okay, like that. You want to find a delta so that you're guaranteed. You want to find a delta so that you're guaranteed to be, so that no matter any value of x in here, you're guaranteed. And then the idea, the best one would be to choose a delta like this, because any value here will give you a value of, if you evaluate f at any of these values here, in anything in this interval, except at this middle point, anything, like here you evaluate it there, that's going to be between here and here. You evaluate it there, that's going to be between here and here. Okay, so if you were to choose a delta that's that comes out to here, then that wouldn't work because this value here would give you something outside the region. Okay, so that's just the basic idea of what's going on. Okay, but I want to show you something really interesting, and that is this other book right here. So before we had this definition of the limit that I just showed you, they used something called infinitesimals. And it was like an infinitesimal was a number that was smaller than any other real number, but yet greater than 0. Okay, and so you can tell that's going to lead to a lot of contradictions. And it did, in fact, lead to contradictions. You know, but they just used it and it was like, oh, it works. And so, you know, it was kind of like, accept this on faith. It works. Back in the day, you know, back in that time, here's a book that was written in 1734. And if you look at it, it says the analyst. So the branch of mathematics that deals with all this epsilon delta stuff and the definition of limit, that's analysis. So analyst. It says, or a discourse addressed to an infidel mathematician. Oh no. So this is like, so back in the day, you know, even you know, you might get this impression, you know, from what people say is, we're so educated now that we know that religion is like all wacko. But people back then that thought, oh, we're educated and we think religion is just a social construct, blah 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 blah. So that's been around for. Now that's not something new that people are just becoming enlightened all of a sudden. You know, this is published in 1734. But basically, the point of this is this is written by, oh dang, who was it written by? It was written by, I can't see very well, but it was written by some guy, his last name is Berkeley, who was a bishop, I think a bishop in the Catholic Church probably, or maybe the Church of England, I'm not sure. But it was written by a bishop, basically pointing out, because like scientists are like, oh yeah, we have the truth. But he's like basically saying, no, you don't. You're accepting a lot of stuff on faith. And here's mathematics, which is like, nobody thinks that mathematics is based on faith at all. But at the time, I guess it was because of these infinitesimals. But he kind of goes through all that right there. And this word right here, fluxions, that means derivatives. And so that's kind of interesting. I thought I would just like show you this. It's like this huge thing on that, and then he refers to Sir Isaac Newton as the great author, and then he also refers to Leibniz in it also. Okay, and so another interesting thing about Sir Isaac Newton, which you probably never heard of. I mean, most people think of him as, oh, he discovered gravity. Well, he's the one that came up with how gravity works. You know, how it's inversely proportional to the square of the distance between the centers of mass of the two objects. But what a lot of people don't realize is that he's probably spent about at least as much time studying alchemy and at least as much time studying religion as he did mathematics and physics. And one of the things that he couldn't, and you can look this up, but apparently he was about to accept a important position at a religious university, and he took this very seriously, and he embarked on a study of the principles of religion if he was going to accept the position. And he came to the conclusion that the concept of the Trinity was incorrect. It was a corruption. that was added later. He came to that conclusion, and it seems like because of that, he declined to accept the appointment. I mean, you couldn't go publicly about these things back then, or you would be in serious trouble. But I think he wrote some things. He wrote some things that made it evident that that was his position, and it came out after his death. Okay, so I thought you'd find that interesting. Okay, so anyways, let's move along and go into the homework exercises. Okay, so here we have, this is sort of the same thing that that I'm looking at right here, where you've got these lines coming up. Okay, so number 1, use the graph of f of x equals x squared to find a number delta such that the absolute value of x minus 1 is less than delta, then the absolute value of x squared minus 1 is less than 1/2. So here they have it right here. So you start from this 1 here, which is the limit, okay? So let me just try to, so this is the limit, okay? And then this is our a right here, which is 1. And the limit's also 1, okay, that's great. And then less than 1/2, that means we're gonna go to 1 plus 1/2 to the limit, from the limit minus 1/2, so it's limit minus epsilon, so that's epsilon right there. The limit minus epsilon to the limit plus epsilon from 0.5 to 1.5. Okay, so the key is to figure out what values these are. So you want to solve f of x equals 1.5 to get that one, and then this one you can solve f of x equals 0.5 because that's the value that you want to get, which is then f of x is x squared, so x squared equals 1.5, or x squared equals 0.5. So x would be the square root of 0.5 here and the square root of 1.5 there. And this is approximately 0.707. And this is approximately 1.225, okay? So this is 1.225, and this is 0.707. And you want to find the distance from 1 to each of these points, okay? So 1.225 minus 1 is 0.225. And then 1 minus 0.707 is 0.293. Okay, so this distance here is 0.293, and this one here is 0.225. So if you take the smaller of these, okay, so you take the smaller of those, that's going to be your answer, because if you take the smaller, then it's going to, when you form this interval, when you form that interval, it's going to be from here to here. Okay, now every single point in here gives you a point in here from 0.5 to 1.5, every point in here. Okay, if we went with a larger value, then this would come out here, but this would come out here, and these points give you values that are more than 1.5, so that wouldn't work. So 0.225 would be the answer to the first exercise. So delta equals 0.5 would be the one that you want to choose. Okay, let's go on to the next exercise. Number 2. So here we have another limit. This is the limit as x approaches 0 of e to the x minus 1 over x equals 2. Okay, for the following limit, find the largest possible values of delta that correspond to epsilon equals 0.6 and epsilon equals to 0.3. Okay. So this right here is our function. Okay. So what I'm gonna do is I'm gonna show you how you can do this using Geogebra. Okay, so here I'm going to put this function in, and remember this, epsilon is 0.6. We'll go with 0.6 first. Okay, so I've exited the screen, and I'm going to, where is it? Okay, Geogebra. Okay, so I put the function in right there, and then here I'm going to put in, so it was 0.6, right? So I'm going to put in 1.4, and 2.6. Okay, so if you go to Geogebra and you come to the graphing calculator or just the calculator, then it gives you this. And then, so here's, as you can see, the limit is, as you go to 0, this does seem to be going to 2, right? This is the value 2. Although if you can't plug in a 0 here, because that's going to give you 0 over 0. But it does just go to 2. It's got a hole there, though. Okay, so if I look here, I can see that it intersects there at, it intersects this 2.6 at 0.2518. Okay, so 0.252, they want to surround it through 2 decimal places. So remember 2.252, and this one right here is negative 0.381. Okay, so the smaller of those, so since we're about 0, we want the closest. So which of those values is closer to 0? It's the 0.252 is closer to 0, right? This value is closer to 0 than the negative 0.381. Okay, so you go with the 0.252. Okay, 0.252, that will be the answer to the first part. Okay, 0.252. And then for the second part, they wanted us to choose an epsilon equal to 0.3. So that means you'd come here and replace this with 1.7, and you'd replace this with 2.3. So this is, so 1.7 is, okay, so 1.7 would be this horizontal line. 2.3 is this horizontal line. This green one is the function, okay? And here we have 2. Now epsilon, remember, epsilon is 0.3. So if you take and you add 0.3 to 2, you get 2.3. That's where I come up with the 2.3. If you subtract 0.3 from 2, you get 1.7. Okay, so you're gonna, so it comes back to adding and subtracting epsilon from your limiting value, which is 2. Okay, so here, this intersects at 1.37 or 0.137. This is negative 0.167. Okay, the 137 is smaller. So 0.137 is going to be the answer to the second part. Okay, any questions on that before I exit out of Geogebra? Okay, so in summary, the first part was 0.252, and then the second part was 0.137. Those are the 2 answers. Okay, according to what I showed you in Geogebra. So I graphed this, and then I graphed 2 plus epsilon and 2 minus epsilon, and then find the intersections and find the closest value. Okay, let's go to number 3. Okay, so here we're looking at the limit as x approaches 4 of 1/2 x plus 4. Now, before, you know, when calculating limits, that's a pretty straightforward thing. You just plug a 4 in right here, and you get 4 over 4, which is 1, plus 4, and that's 5, right? But that's not the proof. Okay, the proof is right here. And what you would do is, here's typically what you would do. Okay, if you're setting out to prove this, you first would start with something I called scratch work, and you would start with this. You start with this, right? And plug everything in. So this is our f of x, and this is our L. So you'd plug everything in. So there's our f of x, and here's our L is 5. And then you would work this down until you get something that looks like this, until you have an isolator like at x minus 4 or something. Okay, so this is 1/4 x, let's see, plus 4 minus 5, that's going to be minus 1, right? Now, I can factor 1/4 out of this, and I get x minus 4. And then multiply both sides by 4, I get 4 epsilon. So then, what this means is if you compare this one with this one, okay, in particular this part right here, we have an absolute value of x minus 4 less than something. And so what we're going to do is, so the way that the proof would go would be let epsilon be greater than 0, and then we would choose delta to be 4 epsilon. In this case, it's pretty straightforward. Just choose it to be 4 epsilon. Okay, but so let's go through the answers here. This one would be, we need delta greater than 0 such that blah, blah, blah. Then this is less than epsilon. Okay, so that's the answer there. Okay, then they're saying this right here. So they're basically going through these steps that I just did here. This happens if and only if this happens. That's just simple, making 4 minus 5. And then if and only if this, and that's just factoring a 1/4 out. And if and only if this, and then so right here, what you're going to put in here is 4 epsilon, which is this choice right here. Okay, and then, so if we choose delta equal to 4 epsilon, right there, we put that 4 epsilon again, then, and we're all done. Okay, and then the diagram, then the diagram is going to be the first one, okay, because, so let's try with the diagram. So, because you've got the 4 here, okay, so 4 is your x value that you're centered about. The limit as x approaches 4. And then you're thinking it's 5, right? So that's a 5 there. And so you have 4 minus delta to 4 plus delta. And then this is going to be 5 plus epsilon to 5 minus, for 5 minus epsilon to 5 plus epsilon. And then your graph looks like this right here. So something like that. So it's just the first answer. Okay, and I think the only thing there is that you want the idea is that you want the deltas down here and the epsilons up here. Okay. So let's look at the number 4, the last one. So this quantity right here. Now here, what you notice about this one is that this factors into this. These factors into this. And then when x is not equal to 7, these cancel off. So this is kind of like just having an x plus 5. And just an x plus 5. So this is going to be the same as the limit as x goes to 7 of x plus 5. Okay, is what it's going to be. But that's not how you prove it. Okay, so let's go through the proof. We need a delta greater than 0, such that if this is less than epsilon, delta, if it's less than delta, then all this is less than epsilon. Okay, so we have this is less than epsilon if and only if this is less than epsilon. That's just factoring like we did here, and that's true if and only if x minus 5. So this is canceling these guys off, x, and getting just x plus 5, and then minus 12 is less than epsilon, where an x is not 7. That's if and only if, and then it's 5 minus 7 is, or 5 minus 12 is negative 7, so it's x minus 7 here. So we get that. So we're going to choose delta equal to epsilon. So equals, so I guess, oops. So that's just equals epsilon. Okay. Because of this right here, so this piece, make that equal to your delta. Just in the previous problem, it was a 4 epsilon that appeared right here when we did this simplification. And so we made our delta equal to 4 epsilon. Okay, so then if this is less than delta, then this is less than epsilon, because delta is equal to epsilon, so that's less than epsilon, and that implies this is less than epsilon. And then we're done. Okay, great. So that was the